Hello everyone, my name is Ismail and I'm from Group 51. This is our project, Video Embedding Powered Language Models for Dental Disease Detection in Uganda. So basically this is the content of this presentation. This is what we are going to look at, the introduction, related work, problem statement and others. So for the background of our problem is we look at dental diseases becoming common, most especially in developing countries like Uganda. So you'll find there are a lot of people with dental problems and they can't access the healthcare, even the healthcare. There are no specialists that can easily assess the problem. So by bringing that, we need a technology that can improve the early detection and reduce a burden of people going to high or expensive hospitals. Then when we got this project, I first looked at some papers that are related to this project. For example, this project talks about CLIP, and CLIP is one of the models that we looked at in this project. Then this one is about VID, and this one is about LAVA. We shall look at how each model was explained, or we based on these papers to handle our project. Then there is also this article that was talked about cameras and embedding to detect some caries, which is a dental disease, and also we are having dental diseases. Then so the problems. So the problem is we have epidemics in low and middle income countries like Uganda. So the problems like caries and oral cancer, we find they are hard for people to access the healthcare, quality healthcare. So, and in the hospitals, there are no tools to diagnose these problems. So for the computation problem for this project is we shall be having continuous video streams. Like for example, someone may open up his teeth in the camera, record a video stream. So we shall be having to compute each frame in real time. Each frame then detect the diseases in real time. Then the other problem is detecting small dental lesions. Like you'll find a problem like cancer. It can be like a tiny dot within the mouth. So to detect it, you need a high resolution image. Then the images, the videos may have like blur, saliva glares, then and camera motions. So those are the problems we have. Then the data sets that are available are based on images, not frames, actually not videos. So we need to okay. Now the computational objective is to minimize the loss, and we get the classification loss. we need to minimize the classification loss, then the temporal consistency loss, and the, the consistency. Then from the computation problems, these are the solutions. We pre-trained a VIT or a clip model, so that will detect each frame, the diseases per frame. Then we make a lightweight. Musirike. Okay, then another solution is to have a lightweight transformer encoder. Remember, we are going to embed these detection models in cameras, so the computation power is not like the normal computers. So we need a lightweight model. Then we need to create. We need to have a low latency. Remember, we shall be having like 30 frames per second. So we need a low latency that can detect all those per frame. So we need at least a latency less than 100 milliseconds. So let's talk about the architecture. So basically, what we did as a team is to get at least 3 models. Then we evaluate those 3 models basing on the project requirements and the computation problems. So we got the efficient net and the vision transformer, actually CLIP, then the vision language multimodal transformer. Okay, now we shall talk about each at a time. Let's talk about the efficient net. This is the architecture. So the efficient net is what it does. It does the scaling. It uses the depth, the width, and the resolution. So the depth is the number of layers in the network. Then the width is the filters that are applied per layer. And this is the formula. So when an image is supplied to this model, it passes through all these layers. This is the linear layer where it transforms it to a linear pattern. Like for example, you have an image with 3 channels, it can normalize it, it can make it linear. Then this is a batch normalizer. Then this is the rectified linear unit. So it passes through this, then goes to this layer. Then this dropout, what does it actually remove some layers, randomly remove some layers. Then this is the final to get an output. There can be more layers as explained here. There is the number of layers. There can be more than this. So we talk about the VIT. So what actually VIT does is it combines both the text and the visual, the text and the visual transformers to encode. So when for the image, it gets the image, then extracts the patches, like it may say 16 by 16 or 32 by 32. Then it depends on the configurations. So what VIT does is you get the image and the text that corresponds to that image. Then the image is extracted, as I said, 16 by 16. These are the patches. After extracting the patches, like for example 16 by 16, then it flattens them. Also remember we are feeding the text to of that image. So after flattening them, then they are sent to the transformer. So the image and the text are stored in the same space. So when another image is sent or is fed in, it checks where or it checks where the space where the prediction is to give you the text or the classification. Then we have the vision language model transformer. Actually, this one we use the lava. Here is the architecture. We get the image, then we pass into the frame encoder, then we get class to a classifier, then we get the output, which is the output that this tooth is diseased or not. Some research questions we said these are some research questions. How can deep learning models be optimized? So we think about optimizing the the models to look at latency. Remember, we are dealing with the fast, like the frame rate of 30 frames per second. So we need to think of how we can optimize the models. Then the performance, we need to what is the performance difference between the CNN and transformer based and language models architectures. Remember, we have three models. So we needed to think about the differences. Then the trade-offs between accuracy, inference speed, and the complexity. Then we talk about the objectives. Then the objectives is to develop an efficient net-based CNN model for static dental image classification, then to implement the vision transformer, then to design a large vision model, and others. Then then the outputs. Okay, sorry. So research outputs. We implemented three models, as I explained. Then we implemented the end-to-end pipeline to detect and classify diseases in a live video feed. Then the detailed analysis. Remember, we are going to make analysis of the video. Then we also made a lightweight prototype. So far we have a web interface, but we are going to implement the mobile. Then let's talk about the EDA. For the EDA, these are the classes we had. We had 6 classes: calculus, caries, gingivitis, mouth ulcer, tooth discoloration, then hypodontia. Then these are the images. We split the images between training, validation, and test. The calculus, these are the images we had: 991 for the training, then 175 for the validation, and the test 130. So this is the distribution of classes in the training for each class that we had, actually to show you the percentage of the images. Then the distribution of images per class, we can see that we had calculus, we had 991 for the training, 175 and 130. You can see for all these classes we have more images for the training and a bit then validation, and the list is for the test. Okay, these are the sample images. We got random images. Each row is the disease. Like for example, calculus is here. This is the image for calculus. Then hypodontia. Actually, I realized hypodontia is just someone who is missing a tooth. Then others. Then, so we talk about the results. For the efficient net, the model that we trained, this is the confusion matrix, and these are other metrics like the precision, recall, F1 score, and the support. You can see for calculus we had 68% precision, then carries we had 99% precision. That's for the efficient net model. This is the training and loss. Training and validation loss. This is the training and validation accuracy. Then we had the custom clip model. Actually, this is almost the same as before. The precision and the confusion matrix. Then we go to the vision language model transform, actually lava. These are the matrices that we had for the models for the model that we trained, and this is the training and validation loss, then the training and validation accuracy. Remember, for the loss, it should reduce, and the accuracy should rise as you train, depending on the epochs. Then we had 20 epochs, so it has to raise, and the loss should reduce depending on the epochs that you have. Then we talk about the model selection. Which model we selected? Remember, we had 3, so we ended up selecting the clip model. Why did we choose the clip model? One, it has pre-trained visual text embedding spaces. Then so we just needed to customize it with our texts, but it has some text pre-trained visual and text. Then the justification, combining clip and BAT text enables the model to understand the context, the contextual description of the object, improving the interpretability. Then demonstration. Okay, then let's look at demonstration for a minute. Remember, we have this is our code. We are going to run our website. We open our terminal. Then we are going to run the web app. It is a Streamlit web app. You run this code, paste and run. Give it a few minutes for it to run. Okay, it opens up the web browser. Then it is going to then we start analysis. A minute before it opens up the camera. Oh, I think there is a bug somewhere. It's because I'm using this camera to record, and as well as I need to use this camera to I'm using it to record here, to record myself. So, and as well as I needed to use this camera here. I think that's the problem. So to use it, I needed to have maybe an external camera. That's why it couldn't work. So, okay, I think that is it for my presentation. Thank you for listening.